How many circles do you see in this region below? Now, I'm not trying to insult your intelligence. I'm sure you can see that pretty quickly. But I want to dive into why or how you were able to count those objects. So I'm sure that you counted them pretty quick and you ended up with 8 circles. And my question that I want to explore here is how do we know that there are 8? So I want to call back to how you first learned to count. You probably used your fingers to count objects by associating each of the objects with a finger. And maybe you didn't use all your fingers, but each of the fingers had one object and you weren't double counting. After this association, you probably associated each of your fingers with numbers, in which case we got an indirect association between objects and numbers. And because we got to 8 when we did this association, we concluded that there are 8 objects. So mathematically, I want to digest this. We can write this as our set of objects is associated to some fingers, which is associated to some numbers. And each of these arrows, so we have collections of objects in the form of sets, and each arrow here is a function. Mathematically, we'll represent it as a function. Okay, so this suggests a definition for counting. So we can say that there are n objects, so n being some natural number, for example, 8, in a collection if there is a perfect one-to-one association or correspondence or function with the objects in our collection that we're counting and the numbers or the set of numbers 1 to n. So we saw that above, that our objects were in perfect one-to-one association with the numbers 1 to 8. Okay, so by association, we mean a function, and we'll write that as f, whose domain is the set of numbers 1 to n, and the codomain is the set of objects that we're counting. And now we have to be careful about what we mean by a perfect one-to-one association or correspondence. And that really means 2 things. It means, first of all, every object that we're counting is, well, counted. So this has a formal name of being onto or surjective as a property of the function f. And our second property is that no object is double counted. So we want an accurate counting. We don't want to double count anything. And as a property of a function, that means it's one-to-one or injective. So there's 2 ejectives here. So these 2 combined make something called a bijective function or a bijection. Bi meaning 2. Okay, so we can kind of condense what we wrote above here and say something like if there is a bijection or a bijective function, f, that goes from 1 to n to our collection, then our collection has n objects. Okay, so that's a strange and maybe complicated definition, but let's see some simple examples to hopefully solidify this idea a little bit. So first, I'm going to ask how many elements in a set that contains the number 1, a square, and an elephant. So of course, you can see pretty quickly that the answer is 3. There are 3 objects in that set, but how do we prove that? How do we show that? And we do that by setting up a bijection. So, or let me just point out that there are several bijections, and I invite you to figure out how many bijections there are from 1 to 3 to our set. But I'm just going to define 1 for now. So f of 1, 2, 3 maps to 1 square elephant, and I'm going to take it to be defined by f of 1 is elephant, f of 2 is square, and f of 3 is 1. So maybe not the most intuitive choice, but there are several choices. And I claim that this function fits the bill for being a counting function. Or in other words, a bijection. And I invite you to check this for yourself, but I'll avoid that here. So because there's such a bijection, we can conclude that there are 3 objects in our set. Maybe we're overcomplicating something simple, but there's more depth to be found in this definition. Okay, so let's do another simple example. How many numbers are there in the set 7, 8, 9, 10, 11, 12? So you could probably visually see that there are 6, but it's a common mistake to take the largest number minus the smallest number, and you get 12 minus 7, and that's 5. But how do you show that there's 6? So again, we're going to set up a bijection. So function from 1 to 6 to 7 to 12. And I'm going to define it by a rule this time. So they are going to add 6 to our input. So f of n is n plus 6. We can check that f of 1 is 7, f of 2 is 8, and so on. And now let's check that it's a bijection. So first of all, I'm going to check property 2. That no 2 inputs have the same output. So in other words, we're not double counting anything. And we can prove that because if f of n is f of m, so if I have 2 outputs that are the same, then that means n plus 6 is m plus 6, which forces n to equal m. So I must have started with the same input. So no 2 different inputs can have different outputs. And now let's check property 1, that all of our collection is counted. So let's take an arbitrary object in our set that we're counting, so some k in 7 to 12. Then k minus 6 is in between 1 and 6, inclusive. And then f of k minus 6 is just k minus 6 plus 6, which is k. So in other words, all of our objects are counted. Okay, so why go through all the trouble of formalizing counting if it's so simple? Something that we do intuitively. Well, I'll offer 2 reasons for now. First of all, is that not all sets of objects are easily counted. So we need a way to agree with each other on how we count things sometimes. And as a second neat consequence is that we can actually extend this definition in our logic to count infinite sets. And this is one of my favorite topics in math, is counting infinite sets. And there's lots of really amazing stuff that you can do therein. Okay, so I'll end off by offering you a couple exercises to try for yourself. So the first one is, how many even numbers are there from 1 to 49? And 2, how many bijections are there from 1 to 3 to our set 1 square elephant? So this is recalling the question that I had above. So for both of these questions, we need to set up bijections. Okay, so in this last question, actually, we need to set up a bijection from some set of numbers to a set of bijections. So we're actually counting bijections with a bijection, which is kind of neat. Okay, so there's lots of interesting stuff that we can do with counting and bijections, but I'll cover that in a later video.